think that we can start, right? Welcome to the new C++ meetup. I feel like we had a pause of 3 months or 4 months and not only 1 month, because last time I wasn't here, and too bad for me because it was a very good session. It was a code review session last time. And I think that in the future we will try to arrange something similar, because I really like how it worked out last time. But now we are back to our standard meetup format. And today's topic is brief introduction to senders and receivers, and I intentionally added a brief into the title because if you want to have a thorough introduction into senders and receivers, you would need a couple of hours and maybe not 1 hour. But this presentation is intended mostly for the people who never saw, never heard of senders and receivers so far. So for those of you who already are introduced with this concept, too bad for you, you'll probably be a little bit bored, but we will start from scratch with some basic concepts. Okay, but before we actually start, we didn't have this one in previous month, I think, and this is our new logo. I don't know if you like it or not, but there are various opinions. But I must say that I really like our new branding. So the thing that I always like to say, it's very good that we diverged from standard ISO CPP logo, and we are not abusing it anymore, because I think that every new C++ user group just sticks the ISO CPP logo, and yeah. Okay, so disclaimer before we start. As I said, this is an introductory talk. And of course, the assumption is you know nothing about senders and receivers. And third assumption here is that we will deal only with a happy path, and we will not talk too much, at least in the official part of the meetup, about the cancellation. So if you want to talk about the cancellation, stick around later on, and we can talk about it, because I think that cancellation is even more serious topic than the main senders and receivers concept itself. So cancellation is something that is very hard. Okay, but let us introduce ourselves with some basic concepts you already know. When we are talking about multi-threading, what is the first that you think of? So you start with a new project, and okay, of course, multi-threading is the core part of probably every C++ project right now, at least on the backend side. And we use all of these primitives all around every day. So processes, threads, atomics, mutexes, locks, thread pools, executors in some form, some fashion. And of course, as George was presenting on one of the previous meetups, we use lock-free data structures as well. And I think that this is 90% of our vocabulary when we are talking about multi-threading. What is the connection between multi-threading and concurrency and parallelism in general? So there is, these two things are not equal. So it's different. When you think about concurrency and parallelism, you cannot say that this is equal to multi-threading. But let's first compare concurrency and parallelism. And let's define them a little bit better. So let's say you have a task that you want to execute, and you divided it into a couple of pieces, and you execute these pieces on one CPU core. If you execute them on one core, these are definitely concurrent, but not parallel, right? Okay, so you have to have some context switch in between these smaller tasks. If you have more than one CPU core, in general, you can end up with parallel execution of these pieces, not only concurrent. So you will have concurrent and parallel execution. Also, there is one more thing that can be added here, and there is only parallel but not concurrent execution. Of course, it's a missing piece here. This is if you have completely divided pieces and completely divided work between cores, and you don't have any interleaving between them regarding these task pieces. So in that case, you have only parallel and not concurrent execution. In general, when we talk about concurrency and parallelism, we say that concurrency is about the structure of your program and how you will design your software. And when you start a new project, you are trying to see what are the components and modules that you will have and how they will communicate between themselves, right? And when you have all of these pieces together, then you are thinking about, you are basically designing concurrency for your project. So it's more related to the design itself, software design itself, and not about some concrete implementation. On the other hand, parallelism is about execution. So it doesn't mean that if you design your software, you are primarily thinking about the concurrency, right? But if you're able to have parallel execution or hardware which is able to do the parallel execution, then you will just benefit from it if the design of your software is correct, right? So if the design is correct on a single core system, you will have maybe slightly worse performance, but you will just unlock more performance if you have a correct design on a better hardware. And this is something from one of the talks from CPP-Con a couple of years ago. It was very interesting for me to brought up to the people, and that is, what is the execution scheduling guarantee, and what are the different scheduling guarantees in general. So you have three scheduling guarantees, let's say: concurrent, serial, and parallel. And we can go into details, and if it's not clear enough, you can ask questions, or we can speak a little bit later, but I will just state some facts here. That concurrency requires stronger scheduling guarantee than serial execution. I don't know if that's clear enough. I didn't want to delve too much into some of the examples because it will diverge from the primary talk. But in general, in concurrency, you have to have some forward progress guarantee, right? So serial execution, you know how you will execute your task. Execute line by line, right? I mean, roughly said, okay? But when you have tasks which are operating concurrently, then you have your runtime has to provide some forward progress guarantee in order for your software not to end up being blocked, okay? So runtime has to provide that guarantee. And because runtime has to provide that, then you have you need to have stronger scheduling guarantee for concurrent software. On the other hand, parallelism requires a weaker scheduling guarantee than serial execution, right? Which is, I think, more obvious than the previous one. So if you, let's say, do not lock anything or you do not synchronize anything in your code, I mean, there is arbitrary order how your task pieces will be executed. And in serial execution, I mean, you have stronger guarantee, okay? I don't have any fancy cool graphics, but if you put that on one single line, then from one side you will have a concurrency, then serial execution, then parallelism is the weakest scheduling guarantee. Okay, so let's go just a little bit back, 13 years back to C++ 11. Why? Because this was maybe one of the most important C++ standards that brought up various things, not only regarding multi-threading support in C++, but also in general. From that point in time, C++ started to have standardization every 3 years or so, or roughly said. So from C++ 11, then every 3 years you have a new release of the standard. So this was like you had the black hole before, and then with C++ 11, you had a light beam that was able to escape a black hole and to give us something more. And in C++ 11, we got some of the primitives. So threads, atomics, we first spoke about memory ordering, right? So memory model was defined, not completely defined, but if you want to hear more about that, again, George's talk was more into details about memory ordering, but there are some of the things that were not yet defined or not yet even defined now, but in general, memory order is brought up into the standard. Why I say primitives? Because like with raw pointers versus smart pointers, you can think of these things as raw pointers right now. So basically, we all know right now that we should, if we can, use smart pointers, if we need to use pointers at all, and maybe to leave raw pointers for some sketchy implementation details, right? And in general, we should strive for better abstractions. But in this case, these primitives are pretty much like raw pointers in today's world. So C++ tends to get new facilities which will be built on top of these primitives, or at least some of them, right? And you will not, you won't need to care about raw threads, mutexes, locks in your code. So you will be able to, back again, go to a drawing board and just freely design your software, not thinking about these primitives, but thinking about your workflow and your pipeline. This is 2024, and there are currently some open topics in the standard committee regarding senders and receivers. I just want to mention some of the important proposals more as a reference for you. So after, let's say, this meetup, you can go and find these proposals and you can maybe introduce yourself a little bit better about it. So one of the important proposals. I think the oldest one from this list from 2018 is networking TS proposal. And it was, the proposal was about standardizing networking in C++. And this is a pain point in C++ for a vast majority of people, right? And if you are using some form of networking in C++, then you are probably using something like ASIO, right? Or some similar implementation, but I think the ASIO is vastly used in C++ projects today. So as a proven library, which is, I don't know, almost 20 years around. So it is like proven design, and networking TS is a proposal that was based on ASIO, basically, and it was about to enter the standard at some point, but it didn't. But it was a very important proposal. Then afterwards, senders and receivers are actually proposed in a proposal that is called a unified executors proposal. And I think that is the first time where senders and receivers are mentioned in the end. And this is a proposal that was a base for the current design that will probably end up in C++ 26. I think that if I got right information, it's almost 100% sure that it will end up in C++ 26. Senders and receivers were about to end up in C++ 23, but it was delayed because of some design decisions, but probably it will be in the next standard. And this is a proposal that we are talking about today. So basically, if you want to look into more examples and what are senders and receivers, and you're not disgusted by reading long proposals and long wording, then you can open this one and you can find this one and see much more examples that I will present today. And this proposal is derived from unified executors proposals. This is so boring, I know, but I have to mention this because afterwards you'll probably go home, and in a month, maybe you will open some of these if you want to know the root cause why we are talking about this. And this one was personally interesting for me to mention it. And this is a sender-receiver interface for networking. So at some point, two competing proposals, networking TS and STD execution proposal, didn't get agreement on a lot of things, and the standard committee decided that they will go with STD execution, okay, the later one. And the newest proposal from this year, I think, this interface for networking is about to make a glue between networking TS and senders and receivers. Basically, to build something upon ASIO, let's say it like that, okay, to incorporate it in the sender-receiver model. So you will use senders and receivers, even though you don't know what is it yet. And underlying implementation can be done in ASIO, for example, right? So that is what this proposal, the latest one, is about to give us. Okay. Let's go into some simple examples. Most of these examples are contrived, and I think first mentioned by Eric Nibler also a while ago. I don't know how many years ago now. When you have some async computation, now you can do something like this. You can have a promise. You can create a future from it, right? You can spawn some thread. It's not advisable that you detach it immediately after it. Please don't do that in production code. Okay, but for the sake of the example, you can do that to do an async computation. And when you're about to deliver the result, you set that result to a promise, right? And then when somebody calls get on the future, it will get the result once it is ready, once it is set by the promise, right? So I hope that, so this is basically C++ 11 code, and I will use this as a base point. I hope that everybody is okay with it. So, yeah.
Yeah, why the mutable?
So, why the mutable? Because you have to mutate promise in this case. So you need to have, because otherwise local variables won't be, you won't be able to mutate them, because by default lambdas are const, and you will have a const this, okay, and promise will be a constant object, okay. If you don't mark lambda as mutable, you won't be able to call set value on it. Actually, it's moved. It's moved, but it is part of the lambda object, and because it is a member of lambda object, then by default this is a function. Lambda is just a fancy function call operator, right? And if you don't mark it.
So mutable is related both for outside variables and for integrated variables.
So let's go a step back. Okay. So when you mark your member function in a class to be a const member function, right? Then you cannot change any member of the object, right? And by default, lambda's function call operator are const, declared as const functions, right? And they cannot change their members. And because P here is now a member of lambda object, you have to mark a lambda as mutable in order to be able to modify it, to call set value on it. Yes?
Maybe the confusing part here is that the P within a lambda shadows the P from the local scope of the function, and that's maybe why it's...
I think that you will not even get a shadowing warning, to be honest. But it's when you are moving something into lambda, it's not the first time that I saw that somebody names the variable with the same name. I mean, it's an example, but okay, of course, it's much more clear if you name it.
Yeah, and why couldn't we, for an example, take P as a reference then?
If we get P as a reference, then thread will basically outlive, right? And you have local promise object. Yes. Yeah. I mean, the promise will cease to exist, and the thread will continue to run. Yeah. Hopefully that's okay, right? So you have to embrace it. Okay, let's continue. I mean, please believe me, we have a lot more to cover. I mean, if we are about to talk about these things, we will. Okay, yes.
If everybody's trolling, then I will as well. So even without detach, it will still be, let's say, a dangling reference because this is not a J thread, this is a normal thread.
No.
I should have formed it as a question, right?
Yeah, even so, I have to correct you a little bit. If you do not detach it, right? You have to join it or detach it. If you do not detach it, you will get std-terminate. So don't worry about dangling references in that case. So yeah, but J threads are by default joined. We are going to the next example. So this is how you would like to use your async computation. Okay, so we set the result, right? We get the future, and then we want to do something with it. Unfortunately, and I will not rant about it, there are other people here in the room who could rant much better than me why std future doesn't have then method. But let's say that you are using boost future, then you will have a then method. But for the sake of the example, imagine that std future has a then method. Then you could do something like this. So you have your async computation. You got the result, and you just want to add something to it and to attach, let's say, some continuation, right? And then to do something more and to print the final result. Again, is it clear so far? I mean, disregarding mutable stuff and whatnot. Okay. So let's do something more. This is an interesting example because we attached a continuation once we already started executing our code. And it's interesting that in most of the cases we know which continuation we want to attach to our std futures, right? So if we know that in compile time, let's say, then why do we need these runtime mechanism? And the std future only employs runtime mechanism for attaching continuations. And it's a very fat object, and that is why std future is ill-advised these days because it's a heavy memory consumption, and it allocates a lot of memory on the heap. And also, in this case, it will allocate memory on the heap to keep your continuation, right? And it has to be type erased. So probably it will be kept in some form of std function within itself. So in the second part, maybe we don't need type erased continuation, right? And we can provide one directly to the async computation. So what is different from the first example, if you remember, is that now we just immediately, even though we didn't start yet our async computation, we pass what will be the next continuation, right? And then before setting the result, if you see that line with the set value, we will first call continuation, right? And then we will set the value. And then again, we can do something like this. So now we are passing, let's say, lambda as a continuation, right? And then we get the same result. Again, I will ask, so far so clear, right?
Can I ask what's the point of all this? Is it to avoid multi-threading or the operating system, so we get like asynchronous compute result, but without using multiple threads, right?
No. The point of all of these is to abstract away creation of the tasks and the work that you need to do from the actual multi-threading and threads and from the actual execution, okay? So usually people stick together their tasks with threads immediately when they start to design their software, right? And the goal of this proposal is to decouple these things. So to design your code that will 99% execute in a parallel environment, right? And completely parallelly, but you don't want to deal with threads on your own, right? You want to decouple these things.
Can you pull the parallel between this and maybe Python? Because in Python, for example, you can create multiple threads, but they're executed in sequential order because of local interpreter logic, right? So it works similar like this, right?
No, I don't think it's the similar. So you can imagine this as something that you already did in C++, but now you just don't need to deal with threads. You just need to deal with tasks. Okay, so you define tasks and you don't deal with threads. Later on, we will deal with threads, and on which environment this code will be executed. Because nowadays, you maybe want to execute something on CPU, but part of the task graph you want to execute on GPU, right? So, and you want to unify these worlds, right? So you don't want to deal with the exact execution. You want to deal with your task graph, and then later on to decide which parts can be executed, let's say, on CPU, and which parts are maybe better candidates for GPU. So, yes?
An executor is required, right? You need a central executor for this.
Yes, you need to have some form of executor, right? But senders and receivers as a model do not, they define, let's say, executor interface. What should be your executor interface? What should be as a concept? And you can freely implement executor on your own if you are compliant with these concepts. Then senders and receivers can employ it immediately and execute on your executor, wherever it is, on CPU, GPU, whatever.
Yeah, so it doesn't really need to be a central. So you could have multiple executors that execute different tasks. So the whole premise and the problem with the initial setup is that both the creation of the work that needs to be done. So in this concrete case, that would be the lambda in the async computation and the second lambda that we've added using f.then. So those are all defining the work that needs to be done, but it's not happening in one place. And because of this, it's happening in runtime. So in runtime, we are spending time actually creating the data flow graph of the execution. And the whole idea is to separate the creation of the data flow graph, so the definition of the work that needs to be done,
yes,
from the actual execution. So another problem with the existing setup is that we actually don't know whether it's already executing, what's happening, is the execution started, is it going to get started, and because of this, all of this brings multiple different overheads. But we usually, when we're writing programs, we know concretely what's the work that we want to get done. So,
I suggest that we go on and we will talk about it later, because really a lot to cover. So
it's an example of forward progress guarantees, right?
Yes. This is a great example how we do not have a forward progress guarantee. Okay, but we will continue. Okay. So far, we were returning STD future, let's say, from our async computation. And we even don't need to do that at all. So we just spoke about these graphs of tasks, right? And you don't want immediately to execute your async computation. You just want to create it and then to start it later on, right? So this function will just create, will just return lambda, which is able to receive a continuation, in this case, this promise, on which we will set this result. So basically, this is almost the same as the first example, but now we do not immediately spawn a thread or something. We just create a lambda that is able to do that, and we return that back. And then, if we want to do something with it, we can employ some, let's say, algorithm. And this is, now we are going into a bit harder things, so please focus on these and maybe save your comments for later. So we created a lazy computation which is not yet started, and imagine that you have some algorithm called then, some function. In this case, this will be called an algorithm, and you can attach a continuation with, on it. So this is like we had with std future and calling .then on it, right? So far, it's the same piece of code. But now we want to put this lambda, this continuation, into the guts of the async computation that we created. So remember, okay, this is something that returns lambda and it receives a promise, right? And then algorithm will provide some continuation. So this is how a very basic then algorithm should look like. And this is a crucial thing. If you understand this, you're good to go for the rest of the examples and to basically understand what we will get in C++26. So what we are doing here actually, then receives a task, and also it receives some continuation, right? What do we do with it? Again, we want to return something, some task, okay, for which, again, you're able to provide some promise. And if you see, we are wrapping into our task, we are wrapping this continuation, this function f. So let's go back. What do we pass to this lambda? We pass promise, because we need some object to call set value on it, okay? And here it is. We call it then promise here, right? And what do we do here? We provide, in this simple example, two functions, set value and set exception, for example, okay? For happy and unhappy path. And what is wrapped within that promise? A continuation that will be executed, and this is function f, okay? And if you see the implementation of set value in this promise, okay, this is actually calling set value on promise that will be passed later on when we return from the then function. And first, we will call that wrapped function, and then the result of that wrapped function we will pass to the set value of this promise. Didn't explain it so too well, maybe, but this is it. This is these are the lines that you need to understand. Yes, now it's the time to have your questions. now it will be very good if you have some questions.
Should the promise and then be moved to the then promise, maybe? Or
Then promise.
the promise in the lambda that's in the then function, I guess. Should the P be moved?
Yes, it can be moved. It should be moved, but for the sake of the example, it's not so important here. So I learned that it's much better to keep the slides short and code very simple in order to better explain concepts. But you're right. So let's go back if it's a little bit. If you wrap your head around this, so we now get a function, lambda, when we return from then, and we are able to pass a promise. And you see what we are doing with it? We are chaining that promise that we will pass to this lambda with a function which we passed as a continuation to the then function. Okay, we will continue, but after this presentation, go back to this slide. This is the guts, and then we can simply do something like this. But there is a problem here, and the problem is that you remember that we created a thread, that we detach it, right? And if you remember in the first example, I called .get on future in order to get the value. Calling .get on the future will block up until someone sets the promise. But in this case, I will be in a little bit of a problem because this thing is not yet complete because I do not stop. I do not join anyhow after instantiating F2 here. So it is a problem of a sort. So basically, this is the same. So in this case, let's say we are chaining two computations. You do some async computation, you chain one continuation, right? And then you chain another one. And I wrote it in 2 lines in order not to have these inlined then calls. It will be harder to follow. But the thing is that, as I mentioned, we are not blocking anymore after F3, right? We need to block somehow and wait for the result. And that's why we need some they call it a sync object. So we need some object which is aware of this condition, which is able to block up until it gets the result. And as you can see, we pass that sync object again as some form of promise. And there is another important algorithm. So we mentioned only one so far. This is then algorithm. Another important algorithm, which is exactly called in the proposal like here, is called sync wait. And sync wait is basically something that blocks and that waits for the result. So imagine you built a graph of tasks. You didn't start the execution yet. At some point, you start the execution, but you want to wait for all of these things to complete and to get the result. You will sync wait on this combined task, okay? And then after calling sync wait, if you look at the signature of this function, it indicates that sync wait actually returns a value, final result, some t. And then remember what we passed using then algorithm. In then algorithm, we passed then promise to the task. Here, what we are doing, we are passing something that we will call sync wait promise. So again, the same scheme, sort of. But sync wait promise is a little bit more complicated. It has a state, okay? And here we call it sync wait state. We will see what is it. And also, what is important here, we will actually wait for this state to change, which is an indication that we got the result. So this wait on the conditional variable here in the state is actual blocking. Okay. So when async computation is finished, when it finally sets the value on the promise, somewhere along the road, we will get the value and the state will be notified. Okay? Yes?
Where is the task parameter used? I don't see in code. I don't. Oh.
Okay.
Just blue and
yeah, sorry about it. So I'm using a new presentation system inspired by George's presentation, and I really like it, but I didn't had enough time to change the default theme for it, but I will do it. With probably, yeah. Yes?
Does this have any connection to signals and slots from Qt framework or similarities?
No. So signals and slots are, slot is just a callback. And then when you, in Qt, you can raise a signal, right? And particular slot will be, for that signal will be executed, if I'm right? Yeah. So, sort of, but it mimics something like this. Okay, when we notify, when we call notify on conditional variable, this thing will unblock and continue with the execution. And when it continues with the execution, we finally, on the last line, on the last return, we return the result. Yeah. And because we had a lot of questions, this is also part when, if you have a question, please ask, or forever stay silent. But the thing is that when we set the value, we want to notify that the value is there. So that's why here, remember, the signatures are the same. Again, we have a set value and set exception methods on this promise, right? And set value does what exactly? It will actually set a particular value into the state, this shared state, which we are using within this sync wait promise, right? And we notify. We say, okay, we have our result ready. Okay? And back there, this code will unblock and state will contain the result. And if I need to say what would be the good thing is that to bring with you after this meetup are these couple of slides. So please, so from the then algorithm to the blocking mechanism with sync wait promise, if you analyze that, then you're really good to go to understand the concept itself. Yes?
And just to confirm, so these algorithms are in the proposal?
Yes. So these are really contrived examples and not production-ready things or whatnot, but actually this is how they are implemented. This is how then algorithm, for example, is implemented in the proposal. I'm not sure about sync wait. Is it really implemented using standard mutex and locking like that? Okay, but the concept is 100% the same. You have to block somehow, but it's not really important how do you do it. It's important that you do it. Yeah.
So we have F, which is asynchronous computation, and we are chaining a computation which is not asynchronous with them.
Okay.
How do we chain to asynchronous computations?
How do we chain?
To asynchronous computations.
We can use, yeah, so we can, it's a little bit sketchy question. Why? Because you have async computation, and then if you want to chain, again, async computation, you can do it like this. Why not? I mean, but it doesn't mean that you need to execute it on the same executor, right? You can decide. If you don't make any decision, it will probably be executed on the same executor that you started from. Okay? So let's say that you have a thread pool, if I understood your question correctly. Let's say that you have a thread pool. You are using a thread pool as a working environment for your task execution, right? You start some async computation, and then at some point you want to chain, but you want to chain async computation once the first one is finished, right? So they will not run concurrently. So this is important thing. So one async computation will be finished, and you can freely attach another async computation. The only thing is that in that case, you can choose in between where do you want to execute it. You don't need to execute it on the same thread pool you started from. Okay? That's the difference. Something else. Yes, I don't want to mention that. I have it in the examples later on, right? But you will not. Then algorithm is used to chain continuations that will be executed in the same context as the task on which you attached the continuation. Yes, yes. Okay. This is the important bit here, right? So we had some async computation, we chained some other function, and then this is the final important thing in order to block is to call sync wait on this, and we get the result. And from the usage perspective, this is how you would use algorithms. Yes? Yes, sure.
Just maybe to clarify, like everyone here understands what an executor is in this context. Maybe if someone doesn't understand, like maybe you can raise your hand. Okay, everyone understands. So in this case, sync wait will launch our task, right? Because so far
yes.
it was lazy. We didn't do any
yes.
work. And the issue is, in practice, sync wait is kind of a bit useless because you make your async task and then you wait. It's maybe not the most useful thing. And in the proposal, they give us a lot of attention to not detach your task. When you launch an async operation, you need to keep the state. You don't want to detach it. You need to keep it at hand. And in the proposal, there's a special structure called async scope, which allows you to push task into it. And when a scope where this async scope lives goes out, only there you will wait. So you don't need to like wait each time you launch an async operation.
That's a good point. So
yeah, and one more thing. So you mentioned GPUs, right?
Yes.
So in this whole storyline, they would be a part of another context, right? Another execution context?
Yes,
or
yes, of course. So, for example, for this proposal, there is an implementation from NVIDIA, stdexec library, right? And you can today fetch the library, and if you have at home NVIDIA GPU, you can also use their C++ compiler, NVIDIA's C++ compiler. You can compile your code with stdexec library that I'm just mentioning, and I will mention a little bit more. And if you do that, if you use their compiler, you will be able to use dedicated executors for NVIDIA GPU. And you can really try out and execute. I mean, these tasks are meaningless on GPU, but you can do that even today.
And so you have one context, which is like a thread pool for the GPU, and one context, which is a thread pool for the CPU. And you would need something like, even mentioned, like chaining async tasks in order to switch between them, right? To move the result.
Yes, you have some other algorithms. We call it algorithms, let's say helper functions and whatnot, that you can use to switch between contexts. So to move from another context to the other one. So if you were executing your task on a CPU and then you want to move with that result onto the GPU and to do some other task, you can do that. It is meant to be used like that. A bit more advanced, but we can proceed. But this is a good point that was mentioned here. So sync weight will be actual thing that will start work here. Imagine that you just erased printf line here, and you don't print your result. The whole graph will be just discarded because it's not needed. So you did not start work yet. You started execution once you called sync wait. I mean, it's meaningful because you state that you need it.
And who is responsible for discarding and destroying the stuff? Who is responsible for discarding and destroying? Executor will destroy?
No, I mean here.
Here it's not discarded, but if I wouldn't start this,
actually is discarded once you exit the main function. So you are responsible.
Destroyers will.
You are responsible of keeping this graph alive.
So destroyers of this F2 decrease some counter of shared state and shared
Let's
state.
say that it's an implementation detail, but it's not.
Yeah, not even that. It's not even started. Like
it's not. Yeah.
You're building your graph before you start the execution, and sync wait is the only thing that starts execution.
Yes.
Here. So it's like you were building your pipeline, but never called it.
Imagine you have a list of objects, but you don't use it.
If you're using ranges library.
It's the same like with the regular list of objects. Let's say that you have here a list of objects.
Destroyers of if F will destroy the resources of the.
Yes, exactly.
Sorry. So you said that in order for anything to get executed, I need sync wait to block my code so that asynchronous operations can be performed. That's a cool design. So in a UI application, if you click, you want something to react on it. You don't want the UI to be blocked until that handler is...
you will be, probably you will be only somebody who will chain, yes?
As I mentioned, there is a special structure called async scope, which you will use in your objects in user interfaces, for example. So if you have a function which will need to call an async operation, it will just push this task into this async scope which belongs to the object. And it will need to wait until all the tasks the object invoked in this async scope when it will go out of scope. For example, if async scope is owned by this object, then when the object will be destroyed, it will wait for all these tasks. Or you can pass an external async scope to this object if you want objects to be quickly destroyed. For example, in Qt, you will use async scope. That's the short answer.
So the async scope will be getting things before it gets destroyed.
Async scope will not require you to block to launch a task. It will only wait for all tasks which were scheduled with it until they complete.
It will basically join them and wait for them.
I'm not talking about when it needs to join.
I know.
the tasks.
I know what you're talking about.
The event handlers performed it as soon as event. Is
Wherever you end up, you can get a scheduler in any place you are. You could be able to get a scheduler and to schedule your task to be executed on that scheduler. So you don't need to particularly wait for it. You can schedule it, and if it's possible for that scheduler, which is attached to a particular executor, if it's possible to run it asynchronously, I mean, truly in parallel to, let's say, assigning it a separate thread, it will be executed immediately. You don't need to call sync wait for that.
Okay, so sync wait is not the only
This is like I mean, if we simply compare this thing, this is like you have message loop, right? So sync wait here is basically while one, I'm just kidding, but basically you run your message loop finally with this sync wait here, but it doesn't mean, so if you run your message loop, that you cannot push some tasks to the particular scheduler or particular executor to be executed. You don't block. Yes. No. I mean, it would be horrible if you need to wait in somewhere in between to call sync wait somewhere.
Yeah,
okay.
but another comment.
Yes.
Of course. So a scheduler is just something that waits for completions of tasks for you, right?
Not really. Scheduler is an entity which is able to pass, let's say, I don't want to say schedule, but pass your tasks to the executor. So you get the scheduler from a particular executor, right? So they are in pair. So if you have an executor, you get the scheduler from it, and you can schedule a task. So it is a glue. You had some comment, right?
Just one comment. Execution resource. So execution resource. The distinction is sadly important.
Execution resource, yes. So, but it is a glue, I mean, between task you want to, let's say, run and the execution resource. You don't execute your task directly using the executor, right? You use scheduler that you got from the executor to do that. Yes, basically it's a lightweight interface of the executor. Let's be imprecise, but it is like that. Okay, we just spoke about executors, and here is one executor. If you remember, we spawned a thread within our async computation. So on the first slide, we started by spawning thread within async computation itself. But as one comment was what we are talking about here today, we want to separate the concerns, right? So you want to separate your task creation and your computations from the actual place where this will be executed. So if you think of now as the async computation doesn't mention a thread anymore, right? So now a new thread will be our executor. It will be something that is able to receive a promise, and new thread will actually decide where it will execute, and it will spawn a new thread. Async computation doesn't have anything to do with it. And if you see first line of the main function, we call async computation with that, thank you, with that promise. And now async computation is completely detached from knowing where computation will be executed. Okay, so this example now shows that computation and continuation, which will be attached with the then function, okay, will not be executed on the main thread, but it will be executed on the new thread created here. Okay. Whew, done.
While they're there, may I ask you, could we reuse the then combiner to combine the new thread creation with the async computation, and then combining it with the same then? Sorry, there is like a lot of then.
A lot of thens.
Let's distinguish them. Then I will call this combinator.
Okay.
And, with this then combinator, we can combine first operation, the thread creation. It's like this scheduling, and we can call then async computation. Then new thread async computation.
I think that I understood, but we are doing that with a different algorithm. We are not doing that. It's not meant to be done with then combinator. Yes, it will be a different then. It will be called on, and there is some other algorithm also that you can use that basically serves for that purpose. Okay, to make async computation as a continuation for the new thread creation, if I understood you correctly. But we are not using then, we are using a different function, different algorithm. It's not meant to be, yeah. So this is. Let's jump forward. So this is important thing. Async tasks can be composed without allocation or almost without any allocation. So whatever you saw here is not type erased and doesn't use any dynamic allocation, which is good. So if you know, let's say in compile time, your tasks or your graph that you will be executing, you can do that without any particular dynamic allocation. And what we kind of learned here is that composition using then or blocking using sync wait are just algorithms, just generic algorithms. Can be implemented in different ways, but you just think of as any other algorithms, right? Okay, so this is the link for the actual proposal. The first sentence from the proposal says, it is a self-contained design for a standard C++ framework for managing asynchronous execution on generic execution resources. This is basically what we were talking about here. So the idea is that we completely decouple our tasks from the execution resources, right? Some motivation about it. So if you used ranges so far, this will look quite familiar to you because, I mean, I don't want to mention that it is the same creator behind this, but it is. Eric Niebler is somebody who is one of the persons who is behind all of this, and he is the designer of C++ ranges. And this feels pretty much the same. You will see later how we are combining the tasks. It feels like we are manipulating C++ ranges. But it's an idiomatic way to express async work. And what is most important here, motivation for them to create this proposal is that we have a lot of different async APIs around. So the problem is that, I mean, I don't want to even go into that on different operating systems we have different fast or dedicated async primitives, right? On Windows, you will probably use I/O completion ports or something like that. On Linux, you will use EPOL, and if you want to combine these two things, it's very difficult. I mean, to unify these things. And also, you pull in a couple of third-party libraries. One third-party library has one signature for callbacks. The other third-party library has, in some way, different signature for their callbacks and the other way how to pass the data around. And if you want to combine these two third-party libraries, it's very, very difficult to do so. So the main motivation behind all of these is for you not to be able to combine these things. And the burden is on third-party developers. So it's not burden on you as users for third-party libraries. It's a burden on them to comply with the new proposal and with the new API. So to integrate themselves into sender-receiver model so that you will be happy and use them together. I mean, this is a story like with C++ coroutines. It pretty much resembles the same thing. In C++ 20, we have C++ coroutines, but do we really have good libraries nowadays that we can say it's a de facto standard after 4 years or so? No, we don't. So I smell that we will have similar problems here if we don't get support from the, let's say, third-party libraries, or if they are late with the integration, then again, you have to do it on your own. You have to glue it yourself. But it is possible. I mean, you have something, and you can glue it on your own, but it would be nice if third-party vendors would do that on themselves. So with C++ coroutines, what we got so far, I think, in C++ 23, we have STD generator. I mean, really, after so much work and so many years, the only thing that is really standardized is STD generator, and that's it. But I mean, not nearly enough for usage of coroutines. Okay. And there was a question: what is a scheduler, right? And yes, this is a lightweight handle to the executor, to be precise, to the execution resource. And this is a wording from the document itself. So lightweight handle that represents a strategy for scheduling work. Senders are nothing more than work that you need to do. These are actual tasks, or what we had in the previous example, our async computation is a sender, right? So something that will do the work. Receivers are callbacks, plain and simple, but fancy callbacks, a little bit better, and a little bit better structured. So if any one of you used ASIO in production, right? You just remember that there you can attach callbacks to this and that, but you end up, wanted or not, with spaghetti code and callbacks that are not easy to analyze or even to comprehend and to localize together or whatnot. Receivers are a little bit better structured, and part of the work which is called structured concurrency. So there was one point before that Colin mentioned here, and that is that we do not want to scatter around our async tasks without knowing when they will finish. So that's why also async scope, for example, is provided. There were a lot of talks even before sender-receiver proposal about async destruction of the objects and whatnot. So async scope tends to be something like that. So if you can contain some async tasks within some enclosing task, then you should do that. So it's very chaotic if you just spawn threads around and you do not have a control on their lifetime. So it would be very nice if you can structure them to join them properly when you need to join, when you need to do that, and then, for example, you're sure you freed all your resources, so nothing is running still after you joined your tasks and whatnot. So structured concurrency in general helps you do that, and what we talked about, async scopes. But with receivers, we only dealt here with the value channel, with set value, but also you're able to provide an error. So for example, if you have an exception thrown in your async computation from the previous example, you will not call set value, you will call set exception, right? And you will set that as a problem. Also, you have stop channel, right? You can cancel your computation. And what is interesting when you cancel that using this is a completely different topic now, but if you using stop tokens, you can cancel complete subgraph of your graph of execution. There are some problems with that. Is it good for them to be so intrusive, these stop tokens? But that's another topic. But you are able to cancel subgraph of your initial graph that you started with. Okay, this is an example from stdexec library right now. And so this is not, I think that I cannot increase the font size right now. I will mess everything. I will mess up everything, sorry. But you can move here. Sorry. But in a nutshell, what we are doing here, I will let you read it, and hopefully it is clear. Right? So As we mentioned, we have some execution resource. In this case, we have some thread pool of any number of threads, let's say 8 threads, doesn't matter. We get the scheduler from that execution resource, and then we start, this is an important thing here, we have to start from some sender, from some work. Initial work doesn't have to be a real work, it can be only creating an execution context. So in this case, here, this begin sender will only serve a purpose for, let's say, spawn underlying thread, as we had with the new thread function, if you remember. So this is our initial sender. This is our begin sender. Just spawn a new thread. And then you want to do a real work, right? You attach continuation, you attach a lambda, and then you want to do something else afterwards, why not? And you want to wait for all of that together with sync wait at the end. That's it. So what we did here, we started some work on a thread pool in one of the threads of the thread pool. Okay, so far so good. Okay. Please don't ask me why do we have angle brackets around I on that line, because we will spend another hour explaining that. Take it for granted for now. Okay.
Why don't they have much easier to
Yes, I mean, it's a syntax sugar, basically. But yes, we can have that. I don't know in which revision it is proposed that we will have pipe operators for that, but we will have that, I think, as part of the proposal. So the comment was that we can call, basically, we can have begin, and then pipe, and then high. I mean, this particular, we can pipe then function call, okay? And then we can pipe another then function call afterwards. So it will look like Unix shell and piping the commands in a Unix shell, right? And the same like using C++ ranges.
Yeah, okay, so I'm not going to ask about the angle brackets, but why do we have dot value?
Why we have?
After
Where?
sync wait.
Don't ask that as well. No, it's okay. But there are basically because you have different channels, okay? You have different mechanisms of getting values and errors from the resulting type. And in this case, you have provided dot value on the result type of sync wait that will actually return. You don't know what. Let's call it, yeah. But it will be a tuple, but yeah, it doesn't need to be. Yeah.
We call value in presence of an exception to rethrow the exception, right?
No, it doesn't. It's not meant to. It will return you, I think, exception pointer, exception underscore PTR, exception pointer. It doesn't. It doesn't. I think rethrows exceptions at all. It doesn't meant to rethrow that. But you will get information that exception happened, right? And you can rethrow it on your own. You will get the exception itself, and you can. You will be able. You can rethrow it then.
But
how I would test whether it was exception or a proper result?
You will get it through a different channel. So when you decompose the result from the sync weight, because the result from the sync weight is a bit more complex object, when you decompose it, you can positionally see that you got an error and not a value.
Is there an example in code?
I don't know if I have a particular example here, but you have. We can show it later. Okay, and this is, for example, when we have more tasks and we want to wait for them all to finish, okay? Just one comment here. So this was the question about, here is the answer about then combinator and why we don't use then. This is an example where we use on function to attach a particular work to the scheduler, right? And this is example for that. But what is, let's say, interesting here, we have to use, in this contrived example, you cannot just simply say one. You have to use some, let's call it lifting function. You have to create a sender from a value in order to be able to compose later on then function call. And here is a pipe operator. So, and you combine yeah, finally, yes. And you combine all of these tasks together, and final when all algorithm, again, it is an algorithm, and the implementation details are not really important here, how you will wait for all of them, but you will be able to wait for all of them. The idea is that only when all of them are finished with the execution, sync wait will unblock and you will get the result. So this is joining all the work together. Okay. Also, we have too much out of time, but okay. Also, there is a possibility to decide which sender you want to use. You don't need to, which sender you want to use. You don't need to decide that in compile time. You can decide that in runtime based on the value, right? So there is this, again, algorithm called set value. I mean, I have to call them like that. It's better to call them algorithms. You will get more accustomed to that wording. Let value will just create a new sender, right? But it will first, you can check in runtime what was, for example, in this case, the value of I, and if the value of I, in this case, is even, then you will produce different sender, and if not, you will produce another one. What I was told is that let value is the most complex algorithm in the proposal. So all of these examples that you saw, like then, sync wait, even when all. So if you imagine how would you implement when all algorithm, it's easy to do that. I mean, we already saw sync wait. When all is just a little bit more complex, not more than that. But let value, again, as I'm being told, is the most complex one because you have different paths how you can go. So we are just talking about the value channel here, but if we are thinking about error channel and cancellation channel, then there are various ways how let value can operate and which sender should be returned from it. So But the let value, again, is a function that will, in runtime, again return a sender on which you can attach some other work. Okay. I think that this is the list of the most important algorithms. So if you start and play with this library, I would suggest that you only deal with these functions, these algorithms, and then when you get accustomed to that, you can see what are other algorithms that are in the proposal. I think that stdexec library from NVIDIA is a library that is in line with this std execution proposal, but there is another library, a bit older one, libunifex from Facebook. And libunifex is more based on the initial Executors proposal, and now it deviates from the newest one, from the newest proposal. But if you look up for the libunifex, you will see, I think, 50 different algorithms, and it's really complex, and you can create very complex pipelines within it. And a lot of these algorithms will be, I think, moved to the standard, but so far they are not. So the proposal itself defines much smaller subset than you have in libunifex. Why I'm mentioning libunifex? I think that libunifex is, I mean, at least they said so. It's really running in the field, so it's really powering up Facebook and Instagram on the mobile phones. So, I mean, it's not so important thing in our lives, or maybe it is, but it is used in the field. It's used in the practice. I don't know, maybe we don't have time for some other interesting stuff. Let's go with this. So I will just mention some things here, and you can use them as a reference. A lot of these things that we talked about is based on some theory, and continuation passing style is something, if you're not familiar with it, this is pretty much that, and that is that you do not return a value from a function, you pass a continuation which will receive the result, and so on. Monads, I don't want to talk about them because we have a person in the room that is able to talk about them all night. Yeah, so continuation passing style is something that is not a new thing around, so it's very old. Okay. This could be an example of continuation passing style. So you do not return a value from a function, you just pass a continuation, and then the result of the operation itself you pass to that continuation. We will not go into these details as well, but sender is a monad, and actually 3 monads composed into a sender. Ivan is nodding, I don't know why, but okay. Yeah, so I will just mention these things because it are on pair with what are monads. So what you saw with that just function, we need to create from a simple value, we need to create a sender. So it's sorry. So basically, it's a pure function which will do the same thing for monads and lift it into a monad. Of course, then is just an f map, and then let value is a bind.
Could you please say out loud what's the let value?
Could you please say out loud what's on let value on the description?
Okay.
It's interesting to hear you how say it quickly.
It sends what is returned. Okay. I mean, it is true, we can dissect it, but I will say it. It sends what is returned by a sender, returned from a function that takes its argument from the previous sender. And do you want me to dissect it right now?
Oh, it makes sense.
It doesn't make sense. It doesn't make sense at all. I mean, but if we go back to the let value, after the recording, we can dissect it, but we already are too much over time. But I understand. It's Ivan, remind me, but monads are just functors in, okay.
I'm just going to say let value is the other than.
Is the other?
Is the other than that mentioned. The one that changes the continuation, that returns a sender and not a value. So in essence,
okay.
N is what transform is for STD optional and STD expected.
Fmap.
Let value is and then on STD optional and on STD expected.
Sure?
Yeah.
Are you sure? Okay.
Bind is and then, and fmap is transform. In every other thing apart from senders.
But this is actually it. So let value is a bind, right?
Yeah, but it's usually called and then in C++.
Okay. No, of course, but...
And this then...
Yes.
Is usually called transform.
You just got my heart stopped. I mean, I believe you, but... Okay.
Sorry, there are 2 senders mentioned.
There are 10 senders mentioned.
Okay.
But
previous sender it was before pipe.
We can dissect it really after the recording is finished, but it's just it's not needed for day-to-day use. I mean, it's some theory on which senders and receivers are based, but of course I can explain in the previous examples what this actual sentence means. I have some more examples with branching, and of course, let value is again used to do that. I will just maybe skip these things because it's too much. But what I can mention here, there is a very good example which is still alive on Godbolt from Eric Niebler. And Eric Niebler wrote a synchronous read file on Windows using I/O completion ports, and he accustomed it to use senders and receivers and stdexec library. And more on that, stdexec library supports out-of-the-box co-awaiting of the senders that they have. So he also used coroutines. So this is like combined example of what we talked about here. So you can execute it on Godbolt and debug it over there. It's too much. Okay. Maybe some more statements here. We talked about a couple of months ago, I think that Peter was a person who always liked to say that senders and receivers are not the same or not on the same level as coroutines, or vice versa, that coroutines are not able to match senders and receivers in what they can do, and he is right. I mean, coroutines have only one channel, let's say, and support one channel. On the other hand, senders and receivers support multiple channels, but all of the things that you can co-await, all awaitables, they are senders, but the vice versa doesn't hold. And it doesn't mean that all senders can be or cannot be easily transformed into awaitables. And what I mentioned, I am kind of afraid that we would need to see support mainly from third parties, from all of the people who are writing async libraries to accustom themselves to the new sender-receiver model. But this will be something that will be in the next 100. Thanks. And maybe you stopped the recording? Questions? Yes, questions, sorry. Questions. Okay.
Okay, I have several, but I'll start with this. How do you debug this? Basically, because of the way that different tasks can be allocated to different execution resources, and the graph itself being analyzed at runtime, and then it being very hard to predict at compile time what's actually going to happen. Is there a way that makes it easier to actually debug this kind of code?
I think the short answer is I don't know. You can, of course, but the problem is this is like a huge expression template. And first of all, this is very awful in terms of what are the return types that you get from these function calls. So first of all, I don't know if it's easy to debug it on that level, right? Of course, you will get, what it's even worse, you will get a lot of inlining, and you will not be able to maybe mentally map what you wrote in the code and what ended up being compiled when you step into different parts. And I think that's not different for debugging than any other multi-threading things that you have to debug. I mean, I don't see any particular difference. So whatever you used to do for already, you can apply here. The problem is that types and objects on which you are operating are cumbersome to remember and deduce who is who.
So we're getting into the territory where we need compile time loggers.
There was it's not Apsel, it's I forgot the name, and I forgot it was a Hungarian guy who wrote. What's the name?
It was the student of
Zoltan. I forgot the name, but it was a Hungarian guy. Yes. Yeah. So there was a Hungarian guy who implemented a CLI, command line interface, basically, and you could, in runtime, I mean, dissect templates and instantiate them, and you could see types that are created, and you can destruct them, decompose them, and whatnot, and to play with it, and to easily understand what is happening with the expression templates code. But I don't think that, I mean, the thing is that we need this kind of tooling within our IDEs, or I don't know, within our tools that we use. We don't have that, I think. I don't know. Sorry? Oh, yeah, okay, I don't know.
Sorry, another one. How does this fracture the ecosystem in a way that actually, for instance, async in Rust does, where you have a problem that some async and synchronous code are fundamentally incompatible, and library, if you use a library, you have to make sure that it's of the model that you actually want to use. So, yeah, do you expect that this will actually result in similar scenarios?
I did not understand the question.
I think the answer is coroutines already did that in a much larger scale because it's a compile time thing.
What was the
So the question was, does this introduction to the standard fracture the ecosystem where you have functions that are async and others that are not, and you cannot
yes,
compile like
yes,
the red
yes.
and blue functions concept?
Unfortunately, yes. I mean, maybe not to the same extent as coroutines did, because unfortunately, when you are within one coroutine, you are stuck with everything that is underneath to be coroutines as well. And yes, from the API perspective, that's bad, but yeah. It's the same, almost the same with senders and receivers.
Thank you.
Yeah, so I have a different question. In the desugared version of the example, the sugared example, what happens if you call then multiple times on the same object or the sender?
Which one? Or somewhere in the beginning, or
Yes,
the
first example of the exec, NVIDIA exec.
Okay. Just a second.
Yes, so there, if you would call them, let's say twice on begin, is that because in the sugared version you cannot do that because you have pipe operator, but here you're able to call them twice on the same thing.
I don't know, but naturally I think it will overwrite, and I think the second one will be used. Yes.
So since you don't launch any work before you explicitly execute the task, you can reuse the senders any amount of times you can. Like you can use create as much task from high sender as you want, and the state which will be used when the task will be executed,
The last one.
it will be the last one. Yes.
The last one.
The one which you pass to the execution. For example, in this case, it will be 8 or 42. The point is that you create state with each sender, but when you nest them, you create a new state. And the only state, it's a state which is composed of all the nested states of every single sender you use. But it's like a separate value. So
Okay, so does it are you able then to call another sync wait on different branch of the state?
yes,
Yes.
because you make a copy of a state. Like each
Yes.
time you create another sender from another sender, you make a separate state.
Senders are self-contained, basically. So it's completely different branch.
Copy down the root, all this copied.
Yes.
Yes.
Okay. So it's not a graph, it's two copies of two copies. Okay, they are independent. Copies.
You make a copy of a graph.
It's not a dynamic graph. All
Yes.
of it is just nested in one big single class with a lot of templates, like parameters. That's it.
So we can say that it's not about laziness, it's about just separate object which self-contained all of the tasks which is needed
It
to
is a-
resulted well to get resulted.
It will be lazy. So if you don't need the result, or if you don't sync
I
wait
mean,
for it,
in
this-
functional way, lazy means that lazy used to describe some algorithm, and it's assumed lazy is useful that if you don't need something to calculate, it wouldn't calculate. In that case, that's not that's not the feature of this laziness. The feature of this laziness is only to postpone starting the whole graph of tasks.
Yes, and in the end, if you don't need at all to execute some piece of work, it's lazy in a sense that you won't spend resources on that, on what you don't need, what you...
But in functional languages, we deliver, we trust language to decide which parts of computation not to calculate, to compute. That's the whole point of laziness in functional programming languages. And in this way, only we decide that, yes, we construct graph, and it seems all the steps we decided, they will be started because we tried to get a result.
But in functional programming languages, if you have indefinite list, you also decide how many times you want to, how many elements, let's say, you want from that list. So you're also the one who will decide how many.
Okay, I mean, yes, but
I mean,
actually functional can kind of decide itself because there is math which functional languages do, so the decision is kind of complicated. Okay.
Thank you,
Thanks.
Goran.
Thank you.